Hey everyone, welcome to the fourth video for section 3.8. So in this video we're just going to go through some examples of problems that you could see or look to solve based on what we've talked about in this section for forced, damped, or forced and undamped oscillators. So let's go ahead and jump right into it. So the first problem we're going to look at is the forced damped oscillator. So solve the ODE, U double prime plus 1/4 U prime plus 65 over 64 U equals cosine of T. And then is this system resonant? So yes, the numbers look kind of nasty, but you'll see why they're that way. It's so some of the stuff works out nicely in the initial steps. If there are problems on exams, I have to figure out how to write them because I have to make one part looks bad, one part looks good, or vice versa. Either way, when you do it in exams, the numbers should work out nice enough that you can do them by hand because I know that you don't have computers on the exam. The other thing that you could be asked is asked about resonance. And if you're asked a general question about resonance, you should know sort of when that comes about, how it works, and be able to show things if you can. And if you can't, then you won't be asked that question. So let's go about solving the system. So we need to look for the really general solution is where we're going to start. So for the homogeneous part, we need to solve this problem. So the roots are -1/4 plus or minus the square root of b squared minus 4 times 1 times 65 over 64 over 2. So I have a -1/8 out in front, plus or minus what's in the square root. The square root is 1 over 16 minus 65 over 16. So it's going to be 1/2 the square root of 64 over 16 with a negative sign. So this in here is 16, which gives me a 4, which gives me a 2i. So I get -1/8 plus or minus i, which means my general solution to the homogeneous equation is c1 e to the minus t over 8 cosine of t plus c2 e to the minus t over 8 sine of t. And so this has quasi-frequency 1 because this is what's inside the cosine term times t is just 1. So now if my right-hand side is cosine of t, I need to guess a solution and then use undetermined coefficients to try to solve it. So I'm going to work out those details a little bit just so you can see what they look like, and then I'll have Maple do a lot of the calculations for me. So undetermined coefficients, u of t equals a cosine t plus b sine t. Note that we don't need to put t's in front of these because for our homogeneous case, our solutions are not cosine and sine. They are e to the negative t over 8 cosine and e to the negative t over 8 sine. So I don't need the extra t's in here because they don't match. Then u prime is minus a sine t plus b cosine of t, and u double prime is minus a cosine t minus b sine t. And then we can plug this into our equation. So our equation was u double prime plus 1/4 u prime plus 65 over 64 u equals, so I get minus a cosine t minus b sine t minus an a over 4 sine t plus a b over 4 cosine t, 65 over 64 a cosine t plus 65 over 64 b sine t. I want this to equal cosine t. So now let's do the equation grouping thing like we had before. So for the cosine equation, I have minus a plus b over 4 plus 65 over 64a equals 1. This is cosine. And for sine, I get minus b minus a over 4 plus 65 over 64b equals 0. So I'll rewrite this as 1 over 64a plus 1/4 b. and this is -1/4 A plus 1 over 64 B. And so now you'd be left to solve these two equations for A and B to get your constants. Now, instead of doing that, I'm going to have Maple do that because at this point we're just solving equations. If you had to solve things on an exam, the numbers wouldn't be this nasty. They'd be a little easier to work out. So let's go run into Maple and have Maple do the same thing. So what I've done here is I've written code that actually does this for any omega you put in. So I solved the equations out for just omega in general, but if I put omega to be 1, if you look at these equations, if omega is 1, this here is 1/64 A plus 1/4 B. This is my 1/4 A plus 1/64 B. So it's the same two equations, and I'm just going to have Maple solve them. And what Maple gives for me is that my R is about 4. So what that tells me is I applied a force of 1 to the system, and I got a amplitude of 4 out of my answer, which there means this system is in fact resonant with omega equals 1. And if we run the code below, which does the same sort of thing, we can see we get that result, where our wave sort of peaks out right around 4 or so. So in this case, we got a resonant system, which is kind of what we expected to see because we plugged in the natural frequency of the system. If I plug in something different, so say I plug in instead, I plug in 5, my R is this time is 0.04, which means I'm getting a really, really squished down solution instead of something that grew bigger than the forcing value of 1. And again, if we plug it in down here, we'll see the same result of a squished down solution. So if we plug in, if we have a frequency of like, say, even if we just do 0.5, so a half, that's still resonant, but not by much. I'm looking here at R bigger than 1. R bigger than 1 means resonant. R less than 1 means it's not resonant. 2 is still resonant. 0.2 is still resonant. A little bit, not very much. But we start going to bigger numbers bigger than 1, and it stops being resonant then, because we're forcing it too fast. So again, the answer you're looking for would be this A and B, but you can see if I plug in 4, this A and this B are nasty fractions, and I would not expect you to solve for those fractions on a quiz or exam. Not at all. And now the second step I want to look into is the undamped case. So I have u double prime plus 4u equals cosine of omega t, and assume omega is not 2. Solve this equation with u of 0 equals u prime of 0 equals 0. So I know my homogeneous equation is going to be, so general solution is going to be c1 cosine of 2t plus c2 sine of 2t plus some u of t. And by undetermined coefficients, u of t is going to be a cosine of omega t plus b sine of omega t. And if I take two derivatives, because I don't need the first derivative, right? All I need is the second one. So let's take two derivatives. I get a minus omega squared a cosine of omega t minus omega squared b sine omega t. And then I want to take 4 of these and add it to this, which gives me that I want cosine of omega t equal to 4 minus omega squared a cosine omega t plus 4 minus omega squared b sine omega t, which tells me that a is 1 over 4 minus omega squared and b is 0. So my solution is, I can plug that in and I get this, c1 cosine omega of 2t, c1 cosine of 2t plus c2 sine of 2t plus 1 over 4 minus omega squared cosine of omega t. And now let's do our boundary conditions. U of 0 equals 0 tells me that equals c1 plus 0 plus 1 over 4 minus omega squared. So c1 equals negative 1 over 4 minus omega squared. And u prime of t is what? It's negative 2 c1 sine of 2t plus 2c2 cosine of 2t minus omega over 4 minus omega squared sine of omega t. And if I plug in 0, this goes away, this goes away. U prime of 0 equals 2c2 equals 0, so c2 is 0. So my solution looks like u of t equals 1 over 4 minus omega squared cosine of omega t minus cosine of 2t, which is what you would expect from what we talked about in the previous video about this with the undamped thing. You get something that looks like this. If I want to rewrite it in the other form, I get 2 over 4 minus omega squared sine of omega minus 2 over 2t times the sine of omega plus 2 over 2t. So that's what you get for the solution here. And then if you were to graph this, you would get some of the stuff we saw from last time. So let me jump back to Maple again real quick to do some more graphs on this, and then we'll be done here. So this is the exact thing we talked about before in the other video. So damping is 0, k equals 4. If I plug in something close to 2, like 1.9 again, I get my beats because I have these slow modulating amplitude multiplying the fast oscillating function. If I plug in something that's far away from there, I get something that I can view sort of as a combination of two sine waves sort of put together. It looks kind of random, but if you jack this up some more, you get basically adding two cosine waves together. And the one case I didn't deal with in that problem because I assumed omega was not 2, what happens at 2, I just get growth because I get a t sine t term coming with my answer. All right, that's it for all these examples. And then in the next section, moving on to completely different stuff, we're talking about systems in Chapter 7. All right, thanks a lot for watching, and I'll see you in the next one.